We saw in the last video the clarity of bee-swarm plots. However, there is a limit to their efficacy. For example, imagine we wanted to plot the county-level voting data for all states east of the Mississippi River and all states west. We make the same swarm plot as before, but using a data frame that contains all states, with each being classified as being east or west of the Mississippi. The bee-swarm plot has a real problem. The edges have overlapping data points, which was necessary in order to fit all of the points onto the plot. We are now obfuscating data. So, using a bee-swarm plot is not the best option here. As an alternative, we can compute an empirical cumulative distribution function, or ECDF. Again, this is best explained by example. Here is a picture of an ECDF of the percentage of swing state votes that went to Obama. An X value of an ECDF is the quantity you are measuring, in this case the percent of vote that went to Obama. The Y value is the fraction of data points that have a value smaller than the corresponding X value. For example, 20% of counties in swing states had 36% or less of its people vote for Obama. Similarly, 75% of counties in swing states had 50% or less of its people vote for Obama. Let's look at how to make one of these from our data. The x-axis is the sorted data. We need to generate it using the NumPy function sort, so we need to import NumPy, which we do using the alias np as is commonly done. Then we can use np.sort to generate our x data. The y-axis is evenly spaced data points with a maximum of 1, which we can generate using the np.arange function and then dividing by the total number of data points. Once we specify the x and y values, we plot the points. Now by default, plt.plot plots lines connecting data points. To plot our ECDF, we just want points. To achieve this, we pass the string period and the string none to the keyword arguments marker and line style, respectively. As you remember from my forceful reminder in an earlier video, we label the axes. Finally, we use the plt.margins function to make sure none of the data points run over the side of the plot area. Choosing a value of 0.02 gives us a 2% buffer all around the plot. The result is the beautiful ECDF I just showed you. You can also easily plot multiple ECDFs on the same plot. For example, here are the ECDFs for the 3 swing states. We see that Ohio and Pennsylvania are similar, with Pennsylvania having slightly more Democratic counties. Florida, on the other hand, had a greater fraction of heavily Republican counties. In my workflow, I almost always plot the ECDF first. It shows all the data and gives a complete picture of how the data are distributed. But don't take my word for how great ECDFs are. You can see for yourself in the exercises. You now have some great graphical EDA tools. You can quickly generate and investigate a histogram. You can immediately get a feel for your data by plotting all of them with bee-swarm plots or ECDFs. In almost every data set we encounter in this course and in its sequel, and also in real life, we start with graphical EDA. Remember what Tukey said, exploratory data analysis can never be the whole story, but nothing else can serve as the foundation stone. In the next chapter, you will build upon graphical EDA with quantitative EDA, which allows you to compute useful summary statistics. With your foundation stone in place, you will spend the last half of this course learning to think probabilistically. You will learn about probability distributions for both discrete and continuous variables, which provide the mathematical foundation for you to draw meaningful conclusions about your data. We will not get mired in mathematical details, but rather will unleash the power of the NumPy random module to use hacker statistics in order to simulate the probabilistic stories and distributions that we encounter. You will find that by writing a few lines of Python code, you can perform even putatively complicated statistical analyses. As you work through this course and its sequel, you will grow ever closer to being able to tell what Tukey calls the whole story. Now let's get to work. We have seen that histograms, bee-swarm plots, and ECDFs provide effective summaries of data. But often, we would like to summarize data even more succinctly, say in 1 or 2 numbers. These numerical summaries are not by any stretch a substitute for the graphical methods we have been employing, but they sure do take up a lot less real estate. Let's go back to the election data from the swing states again. If we could summarize the percentage of votes for Obama at the county level in Pennsylvania in one number, what will we choose? The first number that pops into my mind is the mean. The mean for a given state is just the average percentage of votes over the counties. If we add the means as horizontal lines to the B-swarm plot, we see that they are reasonable summaries of the data. To compute the mean of a set of data, we use the np.mean function, here used to compute the mean of county-level votes for Obama in Pennsylvania. To put it precisely, the mean, written here as x bar, is the sum of all the data divided by the number n of data points. Now, the mean is a useful statistic and easy to calculate, but a major problem is that it is heavily influenced by outliers. These are data points whose value is far greater or less than most of the rest of the data. Consider the county-level votes for Utah in the 2008 election. There are 5 counties that have high vote share for Obama, one of which has almost 60%. Even though the majority of the counties in Utah had less than 25% voting for Obama, these anomalous counties pull the mean higher up. So when we compute the mean, we get about 28%. We might like a summary statistic that is immune to extreme data. The median provides exactly that. The median is the middle value of a data set. It is defined by how it is calculated. Sort the data and choose the datum in the middle. Because it is derived from the ranking of sorted data and not on the values of the data, the median is immune to data that take on extreme values. Here it is displayed on the B-swarm plot. It is not tugged up by the counties with large fraction of votes for Obama. The median is simply computed by calling the np.median function. Now, let's practice using these 2 powerful and ubiquitous summary statistics. The median is a special name for the 50th percentile. That is, 50% of the data are less than the median. Similarly, the 25th percentile is the value of the data point that is greater than 25% of the data, and so on for any other percentile we want. Percentiles are useful summary statistics and can be computed using np.percentile. We just pass a list of percentiles we want, percentiles, not fractions, and it returns the data that match those percentiles. We can do this for all of the swing states. Let's compute the 25th, 50th, and 75th percentiles. Now we have 3 summary statistics. The whole point of summary statistics is to keep things concise, but we're starting to get a lot of numbers here. Dealing with this issue is where quantitative EDA meets graphical EDA. Box plots were invented by John Tukey himself to display some of the salient features of a dataset based on percentiles. Here, we see a box plot showing Obama's vote share for states east and west of the Mississippi River. The center of the box is the median, which we know is the 50th percentile of the data. The edges of the boxes are the 25th and 75th percentiles. The total height of the box contains the middle 50% of the data and is called the interquartile range, or IQR. The whiskers extend a distance of 1.5 times the IQR, or to the extent of the data, whichever is less extreme. Finally, all points outside of the whiskers are plotted as individual points, which we often demarcate as outliers. While there is no single definition for an outlier, being more than 2 IQRs away from the median is a common criterion. It is important to remember that an outlier is not necessarily an erroneous data point. You should not assume an outlier is erroneous unless you have some reason to do so. Since there is 0 evidence of any substantial voter fraud in the United States, these outliers are not erroneous. They are just data points with extreme values. When the number of data are very large and B-swarm plots are too cluttered, box plots are a great alternative. It makes sense then that constructing a box plot using Seaborn is exactly the same as making a B-swarm plot. we just use sns.boxplot. And of course, we never forget to label the axes. All right, let's go have some fun computing percentiles and making some box plots.